In this video, we will be discussing about find building where Alice and Bob can meet. You are given a zero indexed array heights of positive integers where heights of I represents the height of the ith building. If a person is in building I, they can move to any other building j if and only if I is less than j and height of I is less than height of j. You are also given another array queries where queries of I is ai, bi. On the ith query, Alice is in building ai while Bob is in building bi. Return an array answer where answer of I is the index of the leftmost building where Alice and Bob can meet on the ith query. If they cannot move to a common building on a query, set the answer to -1. So what they are saying is that in the input, we are given two things. First is heights and another is queries. So these heights are nothing but some buildings whose heights are given to us. And then we have some queries which denotes us that in which building Alice and Bob is present. So this first value denotes where Alice is present and the second value denotes where Bob is present. Right now, in each query, what we need to do? See, Alice and Bob, whichever position they are present, they can move only towards the right, right? They cannot move towards the left. And then they can move to a building towards the right only when the height of that building is greater than the height of the building in which they are currently present, right? If Alice is present here, then it can only move to the buildings towards the right where the height is greater than 6. So basically, Alice can move either to this building or to this building, right? They don't have to do it contiguously, meaning first it will go to 4, then to 8. No, it can directly go to 8, right? Now, for each query, what we need to do is that we need to make Alice and Bob meet in a common building. And what will be the index of that common building? That is going to be the answer of this query, right? So if we see in this, Alice is present at the building indexed 0, that is here. And Bob is present at a building indexed 1, that is here. Right now, they are in different buildings. We need to make them meet in a common building. Now, what is going to be that common building? So, see, 4 is the height where Bob is present. So, it can move to 8, 5, or 7. But Alice can only move to 8 and 7, right? So, out of this 8 and 7, 1 is going to be our answer, right? So if Alice is here, Bob is here, Alice can move to this and Bob can also move to this, right? So this is one of our answer. Or other thing is that Alice can move to this and Bob can move to this, so this can also be our answer, right? But we need to return the index of the leftmost building, right? So these two were the identified buildings. Out of these two, the leftmost is this building with index 2, right? So for this query, index 2 is going to be our answer, right? That is what we need to do for all the queries, right? So if let's suppose we see this, so Alice is at index 0 and Bob is at index 3, right? So now they can only move towards the right, right? So Alice can only move to 7, Bob can also only move to 7. So the answer of this query will be 5, right? Then if we see 2 and 4, so Alice is here, Bob is here. So see, Bob can move to this building, but Alice cannot move to any of the buildings here, right? So now for this, your answer will be -1, right? Then if we see this query 3, 4, Alice is here, Bob is here. Again, they both can move to this building. So this answer will be 5, right? Then if we see the last one. So now if you see both Alice and Bob are here. Now they are already present in the same building, right? So for this answer will be index 2 itself, right? We need not to move them here and here because this is the leftmost index, right? Where they are meeting. That's why whenever both are at same building beforehand itself, then that building itself is the answer for that particular query. So this is one case that you can explicitly handle, right? So now how are we going to solve this? So see, so for the brute force, what you can do, you will identify for each query that, okay, I'll take this query, Alice is present here, Bob is present here. So I will start from here and I'll move towards the right to identify that which is the first index where the height is greater than both of these, right? So see, why here? Now, in some cases, the second value also can be our answer, right? So let us suppose that we had a query 0, 2. So Alice is present here and Bob is present here, right? Alice can move to this building. And once it moves to this building, both Alice and Bob will be in the same building, right? So in this case, this will be our answer, 2, right? So if we have a query like this, right, where the height of this index is less than the height of this index, or we can say that the height of this index should be greater than the height of this index, then this index itself is going to be our answer. Basically, out of these two, whichever is the maximum one. Now this thing also we need to keep in mind that the index which is towards the right, that should have a greater height, right? If Alice and Bob are here, then this cannot be our answer, right? Because 8 cannot move to 7, right? So out of these two, whichever is maximum, because it is not necessary that Alice will always be present at a position smaller than the position of Bob. It could also be 1 comma 0, right? So out of these two, whichever is the maximum index, if at that index the height is greater than the height of the index which is smaller out of these two, then that greater index will be our answer, right? 0 comma 2, out of this maximum is 2. So if the height of index 2 is greater than the height of index 0, then index 2 will be our answer. Height of index 2 is 8, height of index 0 is 6, 8 is greater than 6, so index 2 will be our answer, right? So these are few base cases that we can check, right? So since we can handle this case and the one we just discussed separately, so whenever we can check for these queries, Alice is here, Bob is here, then we can start checking from here, right? Because when our answer can be this, that case we have already handled, right? So Alice is here, Bob is here. We'll start from here and we'll move towards the right. And whenever we find an index where the height is greater than both of these two, we can stop there and we can say that this index is the answer of my current query, right? But with this, you are increasing your time complexity, right? Because for each query, you might need to traverse the entire heights array, right? So that will give you a TLE. We need to think of some other good approach. So see, what we can do is for efficiently solving this problem, we can see each of these heights. In these heights, if I consider this building and I identify that this index or this building can be answer of which many queries. Basically, first of all, this 8 could be an answer for the queries which are towards the left only, right? So if this is index 2, I told you that Alice and Bob can only move towards the right, right? So this building can be the answer to a query only when in that query both Alice and Bob are present towards the left of it, right? Because only then they will be able to move towards the right and come at index 2, right? So basically for each of these buildings we will identify that okay, index 1 can be the answer to which query, index 2 can be the answer to which query, index 3 can be the answer to which query, right? So for this I should know that before this index 2, what are all the queries? Basically, this index 2 could be the answer of which many queries, that I should know, right? So if I just give the indices of the queries here, this is 0, 1, 2, 3, 4, right? So the heights are 0 to 5. So I'll just write here 0, 1, 2, 3, 4, 5, right? So this building 0 cannot be answer of any of the queries, right? If the query was 0 comma 0, in that case it could be the answer, but as I said, that particular case we will handle explicitly, right? So in this case, for the building 0, there is no query which it can be answer of, right? Then we'll come here. Now here, out of these two, the maximum is 1, right? And here also we have a 1. So at index 1, we will store this query, right? Now what all information are we going to store? So see, what we need to ultimately check, we need to ultimately check that the height of the building that we are identifying should be greater than the height of both of these, right? So if let's suppose Alice is here and Bob is here, so I need to find a height which is greater than both 6 and 4, right? So can I say that it should be greater than the max of these two? So max of these two will be 6. So if a height is greater than 6, then it will obviously be greater than 4, right? So I just need the maximum height of the buildings where the Alice and Bob is present, right? So Alice is present here, Bob is present here. The max height out of these two is 6. So I will store a 6 over here. And I will also store the query index because I should know that which query I am referring to here, right? So I was referring to query 0. So I'll store a 0 over here, right? Then we'll come here. Now here we have an index 2. This one is already done. Out of these two, maximum is 3, right? So this cannot be. Then here maximum is 4. This can also not be. Here also maximum is 4. And then here we have 2, right? So this can be stored at index 2, right? So what are we going to store? So firstly, both Alice and Bob are present here. So maximum height will be 8 and the query index is 4. But as I said, this case we will already handle, right? So this won't be present here, right? Then we'll come here, we have an index 3. So this is the one we can store, right? 0, comma 3. Alice is here, Bob is here, max height is 6. So here we will store 6 and the query index is 1. So we'll store a 1 here. Then we'll come at 4. So for 4, this can be stored and this can be stored, right? So first one is 2, comma 4. So Alice is here and Bob is here, max height is 8, right? So we'll store a 8 here and the query index was 2. And the second one is 3, comma 4. So Alice is here, Bob is here, max height is 5. So we'll store 5, comma 3, right? Then we'll come here. Then for 5, we don't have any query. So this will be empty. So this will be empty. This will be empty, right? This is what we have stored. Now for each building, we know that for which queries it could be an answer, right? Now we need to confirm that which building is answer to which query. For that, what are we going to do? So again, we'll check all the buildings, right? Now we'll also have an answer vector to store our answer, right? So this will be equals to the size of the queries. So queries are total 5. So this size will also be 5. 0, 1, 2, 3, 4. Initially, we can keep all the values as -1, right? And then we will identify that what is the answer for which of the query, right? So now we'll start with all the buildings. So for this building, we don't have any query for which it can be the answer, right? So we'll move to the next building. So for this, we have a query here, which is 6, comma 0. Now, can this building be the answer of this particular query? How are you going to check that? So the maximum of the heights we have stored here, right? The maximum of these two heights we have stored over here. So we need to check that if this height is greater than this height or not. If it is, then this building can be the answer of this query. And if it is not, then it cannot be the answer, right? So here 4 is not greater than 6. Then that means this building cannot be the answer of this query, right? So we will move forward. Now we'll come here. Now can this building be an answer of this query? Yes, because 8 is greater than 6, right? So then that means for the query which is present at index 0, the answer will be the building at index 2, right? So at index 0 over here, we will store a 2, right? And this query is answered now, right? Now for this building at index 2, do we have any queries? No. So let's move forward. Now we are at index 3. Do we have any queries? Yes, we have 6, comma 1. So we have a 6, comma 1. Now can this be the answer of this query? 5 is not greater than 6. So this cannot be the answer. So we will move forward at index 4. Can this be the answer of this query? No, 2 is not greater than 6. So let's put all the queries which are present at index 4. So we have these two, 8, comma 2 and 5, comma 3. And then we will move forward. Now here we'll check, can this be the answer of any of these queries? So see, these queries which I am considering at any moment, I will first check this height with the query which is having the smallest height first, right? Because if this building cannot be the answer of the smallest height here, then obviously for the greater heights also it won't be the answer, right? If I was at this 2, if this 2 cannot be the answer for this 5, then it cannot be the answer for 6 and 8 also, right? So whatever are these queries that I am storing over here, I'll store them in a data structure which always keeps the minimum value at the top. So basically, I will be using a min heap over here to store these values, and it will store these values on the basis of heights, right? So now I will check, is the 7 greater than 5? Yes, it is. So for query at index 3, the answer is index 5, right? So at index 3, we will store a 5, right? And this one is answered now. Then again, we'll check, is this greater than 6? Yes, it is. So for query at index 1, answer is 5, right? So at index 1, we will store a 5, right? And then we will remove this. Now, can this be the answer for this? No, because 7 is not greater than 8, right? So now let's move forward. Now we are done with the heights array. So then that means for this query, the answer will be -1, which is stored already, right? Now you see, one query is already left. Why? Because it was this query. And as I said, before we start all of this process, when we are building this particular grouping, at that time itself, we will check our two conditions, that if both of these are equal, right? So in this case, they were equal, right? So in the answer query, we will update it to any of these index, right? and the other case was that out of these two, whichever is the maximum, if the maximum's height is greater than the height of the other one, then also the answer will be the greater index. So these two cases we will handle beforehand itself before we start all of this min heap process, right? So this is how we are going to solve this problem. Let's look at the code to understand better. So first of all, we need to create a vector for storing our grouping of queries, right? As we saw. So we will create a vector of vector, right? Why? We will see that. So let's name it QS, and what will be its size? Equal to the height's size. Why? Because for each height, we will be storing that it can be the answer of which query, right? Then we need a min heap, right? So we will create a priority queue. Now this will be of type vector int, because as you remember, we were storing two things. One was the height and the other one was the query index, right? That is why we have created a vector int. And since by default priority queue will create a max heap, so for creating a min heap, we will have to write vector int vector in, right? So this is how we can create, let's name it PQ. Then we want to create an answer vector for storing the answer of all our queries. So we will create a vector of type integer. Let's name it res. It will be equals to the size of the queries. So queries dot size, and initially we can keep all the values as -1, right? Then we will start grouping our queries. So we'll run a for loop q equals to 0, q less than queries dot size, and then q plus plus. Now inside this, Alice's position is queries of q of 0, and Bob's position is queries of q of 1, right? Now, as I said, first we need to handle our two cases, right? Which we discussed earlier. So for that, I need to identify that which one is greater. Is the index of Alice greater or is the index of Bob greater, right? So I'll take a variable mini in which I will store the minimum of a comma b, and I'll take a variable maxi in that I will store the maximum of a comma b, right? Now I will check that if the mini is equals to maxi, right? If both are same, then that means Alice and Bob both are present in the same building, right? Or we can put a equals to b also over here. That will also work. So if both are in the same building, or the other condition is that the heights of maxi is greater than the heights of mini. Basically, whichever is the greater index, if that height is greater than the height of the other one, in that case, for the current query, which is q, the answer will be maximum index, right? If both of them are same, then we can take any of them, mini or maxi. But in this particular case, the answer will be maxi only. That is why we have kept a maxi over here. So these two cases we have handled, right? Else, if these two are not the scenarios, then we want to group the query, right? So we will have to store them in this QS vector that we have created. Now in QS, at which index are you going to store? The maximum index, at the maxi, right? At the maxi, we will push back. What are we going to push back? Height, the maximum height, and the query index, right? So first will be the maximum of heights of mini, comma, heights of maxi. We can also take a or b over here. Both will work. And the second thing will be the query index, right? So that is why we created a vector of vector of vector, right? Because we are having this one vector, and then inside that we are having another vector, and inside that the value is also a vector, right? That is why we have taken a vector, vector, vector. So once we have updated all the grouping, now we will check for each of the heights, right? So for int I equals to 0, I less than heights dot size I plus plus, right? Now first we will check that inside our min heap, whatever are the values present, can the current building be the answer of any of the queries in that min heap or not, right? So we'll check that while our priority queue is not empty, right? And PQ dot top, the height will be present in 0th index, right? If this is less than the heights of I, or we can also say that if the heights of I is greater than PQ dot top of 0. So if this is the case, then in the result, the query index is present at PQ dot top index 1, right? So in our query, we'll update it to the index I. that index I is the answer for this particular query, and we will pop it from our main heap, right? And then we also need to push the queries into our priority queue, which are present at index I in QS, right? So we'll run a for loop that for auto LE maybe in QS at index I. Basically, for the current building, whatever queries we have stored in our grouping, those we need to push in our main heap, right? So we'll do pq dot push LE, right? That's all. At the end, we can return our result, right? So let's run this. So here we are running a for loop for all the queries, right? And then here it is running for all the heights. And then inside this, we are pushing the queries into our priority queue, right? Now in our priority queue, in the worst case, we can have all the queries stored, right? So its size will be queue. And we are pushing it into the queue, so that will take log queue time, right? So we can say that the time complexity will be somewhere around q log q plus n, right? And coming towards the space complexity, so here we have created a queries vector equals to the size of the height, right? And then we have taken a priority queue, which in worst case can store all of the queries. So that can also take queue size. And then we have taken another vector, which is of queue size, right? So this is n and the other two are q. So we can say that the space complexity will be order of n plus q, right? Let's submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.